Hello student, welcome back to physics class, and today in this lecture we'll be talking about the topic that is Poisson's ratio. Okay, it is the topic in mechanical properties of solid, that is chapter number 9. Okay, so about this we'll be talking. So here you can see that it is written Poisson's ratio. Okay, before this we have discussed about that what is stress, what is strain. Okay, and we have classified that how in how many ways we can classify stress and strain, okay, depending upon different situations. So in this you can see that it's Poisson's ratio which is written. That means Poisson's ratio itself contains its definition. Okay, this word itself contains its definition. That means it is a ratio of something. Okay, for example, if I consider a wire, which is attached to one rigid support, okay, the wire is attached to a rigid support, and here is the wire like this. If I draw the rough figure, and initial length of the wire, let us say that it is L, capital L, okay, and then what happened? We have applied some force here in the downward direction. Okay, we have applied some force. Let this force be F, or let this force be mg. Okay, if I have m amount of mass in the other end of that wire which is here. So what will happen just by the application of this force? What will happen? The wire will get some elongation like that. That means the length of that wire has been increased now. You can see. Okay, the length of that wire has been increased by some amount, and I don't know that what is the amount. Okay, let this amount be denoted by, if this is capital L, that is the initial length. Okay, so let this amount be delta of L. Okay, that means there is change in that longitudinal length which is there. So that means the wire is under strain, and what type of the strain is it is longitudinal strain, you can see. Okay, so Poisson's ratio is defined as the ratio of lateral change to that of the longitudinal strain. Okay, so what is this lateral strain in this case? Okay, so initially what will happen in this figure, you can see also that in this condition the wire is thick, but in this condition the wire has become thin. That means there may be some diameter of this wire. Let this diameter be capital D. Okay, and now by this extension the wire will become thin in this case, and now the extension has been reduced to D minus delta of D. Okay, this is the final diameter. So that means this much by delta D amount, the wire has been decreased its diameter. Okay, it has decreased its diameter. That's what I can say from here. Okay, so now from here, according to the definition of this Poisson's ratio, it says that it is what? It is equal to the ratio of lateral strain to that of the longitudinal strain. So Poisson's ratio is simply denoted by the term sigma like this. Okay, and sigma is equals to lateral strain to that of the longitudinal strain. And lateral strain means what? Lateral strain means something which is occurring, the change which is occurring in the perpendicular direction with that of the downward force. Okay, you can see that the change in the diameter is occurring here in this case just by the application of the downward force, and this change is along the lateral direction. Okay, it is what? It is perpendicular with that of the downward force, you can see. Okay, that's why I am saying that the change is what? The strain is along the lateral position. Okay, so longitudinal means that is along that of the force. Okay, the change is along that of the force. So longitudinal strain formula we also know, and according to this concept of lateral strain, we can see from our figure also that what we can conclude for this lateral strain. Okay, so lateral strain is what? There is change in the diameter, you can see from here. Okay, so this sigma can also be written as strain means what? There is the change of something with that of the original quantity of that thing. Okay, so here laterally the diameter is changing, and it is changing by delta D. And what is the original diameter? It is capital D from this figure, from our consideration. Okay, and from here longitudinal is what? Delta L upon original length. These all things we have studied, that what is longitudinal strain and what is tangential strain and what is lateral strain and all that. Okay, so I am just applying here in the definition of Poisson's ratio. So sigma can also be written as delta D upon D into delta L into capital L. Okay, so in this way, if the diameter is given to us, if the change in the diameter is given to us, if the original length of that wire is given to us, and the change in the elongation is given to us, so we can calculate that what is the value of this Poisson's ratio. And mostly it is said theoretically by performing different experiments also, it can be said that Poisson's ratio varies from, okay, it varies from 0 point, or one can say it varies from -1 to 1, okay, to point of 5, one can say. This is the value which is decided for Poisson's ratio, that is sigma. That means if I consider any material which is undergoing this type of the process, or which is subjected to this type of the condition, so we can say for that material there will be certain value of that Poisson's ratio, and it varies from -1 to 0.5, which is there. You can see the value at any cost will lie in between this only. Okay, it cannot exceed that. So this is the definition of Poisson's ratio which we can conclude from this discussion. Okay, this is the picturization of that Poisson's ratio. So now let's proceed further. Okay, let's proceed further and let's solve one question on this Poisson's ratio. So students, you can see this question which is written here on this topic of Poisson's ratio. It says that the Poisson's ratio of a given material is 0.20 if the longitudinal strain in the rod of this material be 4 into 10 to the power minus 3, then determine the percentage change in the volume of it. Okay, so what is given to us in solution? Poisson's ratio is given, it is equals to 0.20. First write this, what is given to us, and what else is given to us? The longitudinal strain is given to us. Okay, that means delta L upon capital L is given, and it is equals to 4 into 10 to the power minus 3, 4.0, that means 4 only. Okay, then determine the percentage change in the volume of it. Okay, so that means we have to calculate delta V upon capital V into 100. What is the percentage change? That means the fractional change in the volume into 100. That will be the percentage change in the volume of it. Okay. So we know the definition of Poisson's ratio, and we know the mathematical formula also. Okay, it is equal to the lateral strain to that of the longitudinal strain. That means delta D upon D delta L into L. This we know. Okay, so what we can reduce this formula also into radius form. Okay, we can reduce this formula into radius form also. That means radius is what? Radius is what? 2 times of the radius is the diameter. Okay, so if I place this relation here, so we can get this relation in terms of radius. That means delta R into L and R into delta L. This what we can write. Okay, because D is what? D is what? 2 into R. So 2 from the numerator and 2 from the denominator will cancel out. Okay, so in this format we can write. So now this formula is also important. Okay, so now what we have to do first to calculate volume, we are required to know that what is the value of that radius. Okay, we are required to know that what is the value of the relation of the radius there, or the fractional value of that radius which is here. So if I am applying some force on that wire for the change, okay, so in that case the wire will be in strain. Okay, the wire will be in the state of strain. Okay, so in that case, if I suppose that the V is the initial volume, okay, so the volume is changing from V to delta V. Okay, this I suppose that this is the change in the volume. Okay, when the wire is in strain. Okay, it is feeling a strain. In that case, we can conclude this. So now from here, what we need to do first? First, we need to have that what is the fractional value of the radius. Okay, what is the fractional change in that of the radius? So, just substituting the value of sigma, that is equals to 0.20 into delta r upon r into L. L is how much? Okay, L is not given to us. Okay, so what we can do? L upon delta L, and sorry, this is given to us. Okay, delta L upon L is given to us. That means the longitudinal strain is given to us. And how much it will be? It is equal to how much? 1 upon 4 into 10 to the power minus 3. It is given to us. Okay, so this value we are having. Okay, so now what we do? We just do some mathematical calculation and it will come out to be from here. The value of delta r upon r will come out to be 0.20 into 4 into 10 to the power minus of 3. Okay, so from here we are getting the fractional change in that of the radius just by the definition of this Poisson's ratio. Okay, so from here what we will be getting? We will be getting the value of delta r upon r, that will be equal to, you can see that 4 into 0.20, that will be 0.8 into 10 to the power minus 3. Okay, now we are knowing that what is the fractional change in radius. Now after knowing the value of the radius only, we can define that what is the volume of that cylindrical portion. Okay, because the wire is there, so wire has a radius, that means it is in a form of long cylinder. Okay, it is in a form of long cylinder. So what we have to know now, we will be talking about that what is the volume of that cylinder. So we know that volume of the cylinder is represented by V is equals to pi r square into L. This is the length of that cylinder. And what will happen when any mass is attached to that, or if any force is attached to that wire for that extension, so there will be what? There will be the change in that volume also. Okay, so how much there will be the change in that volume? So if I want to represent this strained volume, so this strained volume will be equal to V plus delta V. And we know in case of Poisson's ratio that radius decreases, the diameter decreases, so radius will also be decreasing by delta r amount, that we have seen. Okay, so how much it will be? What will be the volume according to this format only? That is the volume of the cylinder. It will be equal to r minus delta of r, because r is decreasing. We have seen the figure of that Poisson's ratio. Okay, into, and the length increases. This we know. Is it clear? So name this equation number 1 and name this equation number 2. Okay, so now what we do? We subtract this equation number 2 from equation number 1. Okay, subtracting equation number 2 from equation 1. Okay, so we will be getting here the value of what? Delta V, and it will be coming out pi into, after subtracting, what will happen? This V and V will cancel out. Okay, so after subtracting, you can open it algebraically also. Okay, I am just not I am not having that much of space, so I am doing directly. Okay, I am writing the direct value of this delta V, because we have to subtract. So LHS will get subtracted with this LHS, and this entire LHS will get subtracted from this quantity, that is on the right hand side. Okay, so what value you will be getting? So I solved it and I just want to write it here. Pi into r square into delta L. Okay, and minus 2 pi r into delta r, minus 2 pi r into delta r. Okay, and L. This value will be getting from here. Okay, so now you are having this value, so we have to find what? delta V upon V, this we have to find first, and then we have to multiply it by 100. Okay, so now what we do, we divide this equation which we got, that is equation number 3 from equation number 1. This is a good question on that Poisson's ratio. Okay, so that delta V upon V will be equal to how much? So this will be divided individually. First it will be divided with this, and then it will be divided with this. So delta V upon V comes out to be delta L upon L. Okay, and minus of 2 of delta R upon R. I simply divide this, I simply divide equation 3 by equation number 1. Okay, so what I did, dividing equation 3 from equation 1. Okay, this is what I did here in this case. Okay, so if you divide, you will get this much. So this will be getting divided with the LHS of this equation 3, and this entire quantity will be divided first with this and then with this, and you will be getting these two quantities on the right hand side. Okay, so now we are having the value of delta L upon L. So delta V upon V is equals to delta L upon L is how much? 4 into 10 to the power minus 3. Okay, and minus of 2 into, we are having delta R upon R also that we have calculated, because I told na ki in volume there is requirement of R, so the fractional value of that R I have calculated. Okay, so this is how much? 0.8 into 10 to the power minus 3. Okay, so this will come how much? 4 into 10 to the power minus 3 minus 1.6 into 10 to the power minus 3. So just take 10 to the power minus 3 common and subtract 1.6 from this 4. Okay, I mean 4 minus 1.6. Okay, so it will be coming 2.4. Okay, it will be coming how much? 2.4 into 10 to the power minus 3. Okay, so this is the value of fractional change in that of the volume. So if I multiply this fractional change with 100, then only we will be getting that what is the percentage change in that of the volume. So what we do, we simply multiply it by, so delta V upon V will be equal to 2.4 into 10 to the power minus 3 into 100 for percentage. Okay, into 100 into, yeah, simply I say here, into 100 is equals to this much. Okay, that delta V into V into 100 will be equal to this numerical value into 100. Okay, so now how much we will be getting? We will be getting the value which will comes out to be how much? This will come out to be 10 to the power 2, and this will be any key, it will be coming 0.24. Okay, because this will be 10 to the power 2, this is 10 to the power minus 3, and the base is same, the power get add. So 10 to the power 2 and 10 to the power minus 3, it will be equal to what? 10 into 10 into, sorry, it will be equal to what? 10 to the power minus 3 plus 2, and that's why it will be coming how much? 10 to the power minus 1. Okay, this is the simple maths. Okay, so I am not doing it here, everyone knows. And 10 to the power minus 1 which comes from here, it will be multiplied with 2.4 and to get this much of value. So we are having the percentage change in the volume. Okay. Now let's talk about elastic potential energy in a stretched wire. Okay, what is the elastic potential energy in case of stretched wire? So in case of stretching a wire, what we do some work. Okay, if we are extending that wire from initial length to some final length, and if there is increment of, let us say, small l. Okay, if we consider this type of the figure, and here is the wire, and I have extended this wire to some length. There is some increment in the length, and this is the original length. So this is what? This is small l length which is increased. Okay, so you can say in this case that we are doing some work. Okay, that means by application of this downward force, that is F, to extend that wire, I am doing some work against what? Against the intermolecular arrangements which are there. Okay, if there are molecule inside, because we know that it is a compact structure, if I am talking about the rod or if I am talking about the wire, okay, there are some forces by which they are binded. So we are doing some work against that force. Okay, we are doing the downward work done in the downward direction, work is done in the downward direction against that intermolecular forces. Okay, and that work done which we do against those forces which are there inside this wire is stored in the form of potential energy. Okay, as we have seen in case of mechanical system also, that how the work is done, which is done, is stored in the form of potential energy in case of mechanical system. So here happens the same thing. Okay, so what we do in this case, that U which we are having, that is the potential energy, that is equals to the work which we do in this case. Okay, that is conserved. Okay, that is changed into this potential energy. This one can say whatever work we are doing, that is same as that of the potential energy, that is stored in the form of potential energy in this figure. So in this case, what will happen there is, you can see that there is some longitudinal extension. I am neglecting that lateral one. Okay, so in that case, according to the concept of modulus of elasticity, we talk about Young modulus. Okay, that Young modulus is what? Young modulus is longitudinal stress to that of the longitudinal strain. That means I am applying this force on any cross-sectional area. This has a uniform cross-sectional area, let us say, and this force is directly acting perpendicular to this cross-sectional area, जो उसका circular area है. Okay, so what will happen? I am applying the force on area A. Let us say that the cross-sectional area has the value of A. So this is what? This is the stress. And what it results? It results a strain. That means the original length was L, now the length has been increased by small l. So capital L upon, or sorry, increase in length, that is small l upon capital L. Okay, so from here we can write that F upon A into L into capital L. Okay, so if you want to define force in terms of Young modulus, so we can write it like gamma, that is the Young modulus, this is the Young modulus, okay, into A into L upon capital L. This is how we can write. And let us say that I am talking about x length, okay, x length extension. I am talking about, let us say that wire has reached only this x length, x is less than this small l, let us say. So in that case, what will be the value of this force? This is what we want to know. So in that case, if I am talking about this x extension, which is less than, the wire has not reached this length of small l in this case. So if it would have reached this x length only, okay, which is obviously less than this small l, then what will be the value of that force? So in that case, what will happen? The force will be equal to how much? Gamma into A into, in place of this small l, we will be replacing it by x upon original length. This is what we can write. Okay. So now, what will be the value of the work? What will be the value of this work done in this case? Okay. So we know that work done is what? Force into displacement. Work done is force into displacement. So what we do? We suppose that now we are having this work which is done. Okay, the work which we are doing by this much amount of the force, for very small displacement. Okay, let us say that the work done which we are doing is for very small displacement. That means what we are doing, or not all at once we have just lengthened this wire. Okay, we would have initially we would have moved a small distance and let that distance be represented by small dx that I told many times. Okay, and continuously we are increasing the length by dx, 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 and like that, and then we are completing this length small l. Okay, this I have explained many times. So work done, that means there will be small work done for small increment in the length. That is dx length. Okay, if I talk about dx length. Okay, so for that, this force will be there, which is a function of x, because x is the variable length. You can see x is varying. Okay, and it is varying from, if I consider this to be the reference line, if I consider this to be the reference lines and this to be the final line, so here I consider that the value of L is 0. You can see here is, if this is the starting line, then at this point there is no extension, you can see, and till here the length has been extended to L. That means at this point what will happen? At this point x is what? 0. You can see. If I consider this x to be the variable length, okay, so at this point the value, the extension is what? 0. So x is what? The variable length. It is 0 at this point, and at this point now the value of x has become small l, because it has reached to its final limit. Okay, to its final length, you can see. So what we can conclude from here, that the x which we are using, this is the variable length. Okay, variable length, it is varying from which factor? It is varying from 0 to x is equals to small l, that is the total length to which the wire is extending. Okay, so this small work done for small increment in the length, that is dx. I told them many times when we were studying the motion in a straight line also, that if I represent any quantity with d, that means it is very small. Okay, so this force which we are having into dx, that is the displacement. Okay, this displacement into force, that is the work done. Okay, so from here what we do, gamma into a into x upon L into dx. This is what we have. And now we have to find the total work done in this case. That will define the potential energy, that means work done from x is equal to 0 to x is equal to small l. Okay, that means in this case what we do, we apply the method of integration, because it is the continuous process, you can see. From here to here the wire is continuously increasing. Okay, that's why we apply what? Integration, and integration of this term which we got. Okay, that means integration of this small work done. The small work done will be added like that. Okay, so integration simply means we are adding something in a continuous way. Okay, so from here what we get? Gamma into a into x upon L into dx. And we are having the limits of our integration. That means x is varying from, this length is varying from 0 to small l. That means here the difference integrating value is for x, the variable is x. So x is varying from 0 to x is equals to small l. These are the limits of our integration. So gamma is also constant, a is also constant, because I am not considering any lateral change here. Okay, and length is also constant, you can see. Okay, the given length is fixed for us. So this value will come out, gamma will come out, a will come out, and from denominator L will come out. So what we get? X into dx, and x varies from 0 to x is equals to L. Okay, so from here we get the work which is also equal to potential energy, because it's stored in the form of potential energy, I explained. And this we get gamma into a upon L integration of x dx, that means x square upon 2, and limits varies from x is equal to 0 to x is equals to L. So this we know how to solve. Okay, that means gamma into a will be as it is upon L will be as it is, and first we place the higher limit and we subtract it by putting the lower limit. So if we place x is equals to L in this case, so it will be giving L square upon 2 and minus of the value with lower limit. So if we place x is equal to 0, then we will be getting 0. This is the method that how we solve integration. Gamma into A upon 2 into L square. This is the value which we have for the potential energy. Okay. So now this is very important for us. This value for potential energy of a stress string is very important. That is gamma into A into L square upon 2 into L. This we have to remember. Now let us just convert this value in terms of the physical quantity that we have studied. Okay, let us reduce this required value, mathematical value, in the quantities which we have studied. For example, in terms of stress and in terms of strain. Okay, so for that what we do? We take this value and multiply with L in both numerator and denominator. Okay, capital L. If I place L here also, if I place L here also, then it will have no change in this equation. So we can write that gamma into A into small l into capital L upon 2 into capital L ka square. This is what we can write. Is it clear? Okay. So now what we do? We just split this required expression into gamma into small l upon capital L. This is the first, and small l upon capital L into A into L. This is how we can write. You can see that this is same as this. Just as separated some quantities individually. Okay. So this is what we are getting here. And you know that according to the definition of Young modulus, this is nothing but this is what? This is stress. This is stress. Longitudinal stress. Okay, and this is what? This is strain, that is change in length upon original length. And this is volume. That is area into length is what? Volume. Okay, so we can write that it is what? It is potential energy of a stress string is equals to half into stress into strain into volume. But what happens if I write for a unit volume? Then one volume will be divided and this volume will cancel out. Okay, so for a unit volume, okay, what will be the value of potential energy? It will be equal to half into stress into strain. Okay, this is how we can write. This is how we can write, and this expression is very important. This expression is very important regarding the potential energy of a stretched string. Okay, and further, if I remove this value of stress in terms of Young modulus, that is gamma, that we know, so we can write it like potential energy can also be written in terms of Young modulus, that is gamma, into strain ka square. Okay, stress will be giving gamma into strain according to this formula, that is stress upon strain. Okay, so stress will be giving, this is stress will be giving gamma into strain, this is L. So strain into strain, one strain is already here, so it will be strain ka square. So this is another relation in between different physical quantity that we have. Okay, so potential energy are expressed in terms of these factors also. So the things which I am bracketing here are very important. Okay, so just remember this formula what we are having. Okay, so I hope that you have liked this lecture. If you are still having any doubt, then you can just give me a phone call or you can just ask me in the live class. Okay, thank you.